Hello everybody. This video is brought to you by Asha Akanksha Foundation, and I am Siddharth. And in this video, I will be discussing multiplication of numbers. Uh, by default, now I'll be starting. So I will be discussing first the brute force multiplication of numbers, and then I will be going over what is the time complexity of that particular algorithm, and then I will be introducing a new algorithm, Karatsuba's algorithm. I will be discussing two parts. The second part is a better one, and it is usually used whenever multiplication of numbers is carried out. Whenever the numbers are being multiplied, why, then these algorithms becomes of great value, and the multiplication learning these multiplication of numbers is essentially important because in computers these small differences can improve the speed of any process by a large factor. So I will be discussing the brute force approach of multiplication. So before starting, there will be some I will be explaining what is the input. Suppose that we are given an algorithm, we provide an input to the algorithm, and we expect an output. For example, I am given any dummy algorithm, and we are providing some numbers as input, and we are getting some suppose string or anything, any integer, anything as output. So that black box which is in between, which converts the input to output, that will be called the algorithm. So in this algorithm, multiplication of large integers, in whichever thing I will be discussing, the main things that I will be assuming is that we are provided two n-digit numbers, A and B. That is, both A and B numbers have the same number of digits in them. I will be assuming both of them to be positive, but yeah, you can take negative any of them as negative, and in the end you can just check the sign, either one is negative or both are negative, and on the basis of that you can get the sign as well. So input is two n-digit numbers, and the output will be the product of both of the numbers, and the black box which will do the calculation, that will be our algorithm that we are discussing. So the brute force algorithm is something that we have learned in earlier classes. And in that algorithm, there are two operations. Let me first discuss the brute force algorithm first. So, so in the brute force algorithm, suppose we are provided two numbers, 5, 6, 7, 8, multiplied by 1, 2, 3, 4, and we have to multiply both of these numbers by the brute force algorithm. So in this case, we will perform multiplication. 8 into 4, 32, 3 goes by, and we will perform the calculation in this way. So in when 8 into 4, 32, 2 remains here, 3 goes here, and in this way we perform the multiplication. We fill the rows in this way. These are spaces which are left here, and in the end we just add the columns and get the final multiplication answer. So when you are seeing this algorithm in the most minute details, then you will see that the most basic operation that you are doing is first you are multiplying any two single digit numbers. That is the most basic operation. And then you are also adding, like in this case 3 is being added to 7, 7 into 4. So you are also adding numbers. Essentially, I will take that you are adding one digit numbers, single digit integers. So these are two primitive operations. We either multiply or add two single digit integers. So now I will be discussing the time complexity of this algorithm. Suppose you are performing multiplication for each integer you multiply for each so if you are organizing it in this way, then for each integer in the second row you will multiply it by each integer of the first row, and you are basically carrying out this process for each integer in the second row. So there are overall n multiplications, and so the number of multiplication in the overall process is n. Now what are the number of additions? Suppose we have to remember that if you know the asymptotic analysis, then we take the uh, order of things. If you know the asymptotic analysis, then we take order of things, like if we mean o n square o n square, then it means that any algorithm is taking place in at most c into n square time, where c can be any integer, is any integer. So any algorithm of order of n square is taking place in c into n square time, where c is any integer. This is asymptotic analysis. Yeah, I would prefer if you know the asymptotic analysis previously before starting this video. So in this case, I have to take the worst case scenario in which there are maximum number of additions that I am performing. Suppose for this multiplication, we cannot have any carry because there is no integers on the right side. So we can only start getting carry from numbers on the left side of the first integer to the leftmost. Numbers to the left side, like 5, 6, 7, only these numbers can have carries in their additions. So whenever I will be multiplying, I can have carry in these parts for any multiplication, and hence if there are n integers, then I can have n minus 1 carries for multiplication by one number. Suppose I am multiplying 4 by all these 5, 6, 7, 8, then with multiplication with 8 it cannot have any carry. Then it can start having carry for the multiplication with these numbers. It can be case that some multiplication does not have any carry, but yeah, because we are taking the worst case scenario, we are also counting those cases as well. So in the worst scenario, there are n minus 1 additions for the multiplication with one number. Now for all the n numbers, there will be n into n minus 1 additions, that is n square minus n additions, and there are n multiplications. So in the end, to generate this particular uh, matrix of numbers, this particular rows and columns, we have to first perform n multiplications, and in each multiplication we can at most have n minus 1 additions. So if we can have order of n square calculations to get this matrix. Now what I am getting, I will write here, like if t n, where uh, n is the value of n is the number of digits in both of the input a and b numbers, then please wait a minute. Then the to get this particular matrix, we have to perform n into n minus 1 calculations, and after these calculations are done, we have got this matrix. Now we just add the columns. At most there can be 2 into n columns, because we just in each case, after each row is filled, we just keep appending zeros, and hence in the worst case there can be 2 into n numbers for each row, and there are n and there are n rows and there are 2 into n columns. So once we get this particular thing, then we can just write 2n into n. 2n being the number of columns and n being the number of rows. So this is the time complexity of this algorithm. We can see, if you know asymptotic analysis, we can see that this is of order of n square, and this is order of n square time complexity, which in practical use is not very good thing, because this is a very large time when we scale up in industry. Now I will be with this I have discussed the brute force approach. Now I will be starting discussing the Karatsuba's algorithm. So first of all, before doing that, we should know what recursion is. I hope that you know what is a function and basics of coding, so that this topic will not be too much unfamiliar with you. So suppose if we have you know that an algorithm is a black box which takes an input, any number of inputs, and produces any number of outputs. It is a black box that does that. And yeah, of course, in this course, we are trying to optimize that black box to the extreme and getting the best possible output in the minimum possible time while consuming the least number of resources. So an algorithm that invokes itself again and again on smaller and smaller inputs, it will be called a recursive algorithm. I hope that you know recursion, because it is a very integral part of coding. But yeah, I will be briefly discussing that as well. Suppose that there is a function. It takes any input n, and it keeps on calling itself on smaller and smaller number of inputs, like n by 2, and it will keep on doing this until suppose we have a base case, return if suppose n is equal to 0. Suppose if n is equal to 0, then return something like -1, and else we can just write n by 2. So this is a recursive algorithm. For any recursive algorithm, there are several integral parts of recursive algorithm. First thing is there should be a base case. This is the part where the algorithm stops. There should be recursive call. This is, in this example, this is the base case, this entire thing, and this is the recursive call. And then there is a third thing also. You have to know how to divide and how to divide the problem. Like suppose in this example, we were given function n by 2 plus function n by 2. Then we have decided to divide this problem for n in two parts, for the n by 2 and n by 2. So we should know how to divide the problem. We are taking from n to n by 2. And the fourth thing is that you should know how to combine the results of the recursive calls. That is, if you are doing the recursion, then you should know how to combine both of the results. Suppose this function was originally returning an integer. This is returning -1. Then you should know that whatever value is being returned, you just have to add this value. Suppose in this example we are adding the values, so we know how are we handling the results given by the recursive calls. And yeah, these are the some basic things that you should know for recursion. Yeah, of course, to understand all this you should know first of all what is functions and all these things. After that, I think you might have gotten whatever I've said. This is a recursion. So what will you do? We have taken two n digit numbers, both of them are n digit numbers. We will divide these n digit numbers into n by 2 parts. We take the suppose that this entire number is capital A. Both of the numbers, both of the inputs are capital A and capital B. Suppose this input is capital A and this input is capital B. This is capital A and this is capital B. Then for both of the numbers we divide them into two equal halves. Like in this, if the capital A is 4 digits long, so we are dividing it into two digit numbers, small a and small b, which are of n by 2 digits each. Similarly, we do the same for capital B. We call this part A, B, C, D, as you are seeing. Now there is a so what is capital A now? Now capital A is we take A, we append 10 to the power n by 2 zeros. Like in this case, n is equal to 4. So n this is a 100. A into 100, that is 5600, plus B, that is 78. We take the n to the 10 to the power n by 2 zeros, and then we append them to A, and then we add B simply. This gives us A, and similarly similarly we can get B. Yeah, if you are yeah, for the even digit if n is even, then this process is very simple, as both of the parts A and D are equal, have equal number of digits. Otherwise you can take if the n is odd, then you can either take A to have one less digit or B to have one more, or vice versa. So in this case, to get the multiplication, after that you just have to follow this formula. You just have to follow this formula. 10 to the power, this is 10 to the power. To multiply, you have to just follow this formula. A into B is equal to 10 to the power n into A into C plus 10 to the power n by 2. This is n by 2. And into you have to calculate this plus into BD. This is the formula that you can follow to get the A cross B. This is a formula from Vedic maths. So in this recursive algorithm, the step 1, what do you have to calculate? First thing first, I am discussing this is the Karatsuba's algorithm, first of all, and I am discussing the first part of the first version of the Karatsuba's algorithm. Yeah, to get this formula, you have to calculate AC into AD, AC, AD, BC, and BD. And suppose you have got these numbers, then you just have to append 10, 10 n zeros in front of after AC to the right of AC, n by 2 zeros to the right of both AD and BC, and yeah, of course add them. And yeah, you have to append no zeros after BD, and then you can use this algorithm. So initially you were given two numbers, capital A and capital B. Now you have split the capital A into 10 to the power n by 2 into A plus b, and capital B into is equal to 10 to the power n by 2 into C plus D. Now you were given both of these numbers. You have got A and B, C and D. Now you have got A, B, C and D. Because after splitting these parts, retrieving these parts is a simple thing. You can do it easily in coding. Now you have got this. Now you have to divide your main problem into simpler problem which operates on the same principle. Like initially what you were doing, you were multiplying two n digit numbers, right? N digit numbers. Now you have to uh, divide this problem into smaller version of this same problem, simpler version of the same problem. What you will do, you in that formula you needed what? In that formula you needed AC, AD, BC, BD. AC, AD, BC and BD. What is this problem essentially? You are just multiplying two n by 2 digit numbers in each of them. So this is a symbol that you can use recursion here, and we are using recursion here. And then you just get these things, and then you can just use this formula to calculate this thing. So this is the thing. Now I will be discussing the time complexity of this algorithm. The runtime of this algorithm, which is for multiplying two n digit numbers. What you are doing, first of all, when we are talking about two n digit numbers, and our base case was that we have to multiply as two single digit numbers. So if we specify that particular base case, then we can just use base case n equal to 1, that is multiplication of two single digit numbers as the base case. In that case, we can just simply perform the multiplication, and for two, and then you have to just calculate two recursively these things. And for appending in computers you can easily append with just a single expression, multiplication expression, relational expression, and then you can just add all of this. So in addition, in the worst case, there are n numbers that are to be added in the worst case. So you can just take c into n, you can just take c1 into n for the addition part, and this part is the total work done outside the recursive calls. Why? Because in a particular tn scenario, first of all, what do? You are calculating these four things, and then so suppose the time taken for multiplication of two n digit numbers is order tn, then time taken to multiply two n by 2 digit numbers is tn by 2. We are doing the same thing four times, so this is 4 tn by 2. And yeah, you are ignoring the plus ones, that is carries and all this. And then after you get all these things, you are just adding. Now addition, in the worst case, how many single digit additions you have to do? You are taking AC and appending n number of zeros to the right of it. So you can just say that at worst case, you are just adding n number c into n number of times, any n number of times, and you can just take ca. C is a factor which has been introduced to take care of any unnecessary things which have not been accounted for in the algorithm. And then you just add both of these things. This is n by 2, and this is the time complexity of this algorithm. So This is a fairly good time complexity as compared to the brute force approach, and that is known as Gauss's trick. And so there is still a way to make it better. That is the Gauss's trick. What do you do in that case? Yeah, in that case also you use the same formula. Uh, this same formula. The main things, there are several steps involved in that particular technique. The main things are, first you take AC, you calculate AC, then you calculate BD. These are the two things that you have to calculate, uh, which is the same as in the first version of the Karatsuba's algorithm. Now, for the step 3, you calculate this number, A plus B, C plus A plus C into B plus D. In this case, you are adding two n by 2 digit numbers. So the time complexity of doing that will be C into n by 2. And then you are just multiplying two n digit numbers, which is the same as any two of these things. And in the step 4, suppose you just in the step 4 you just compute this 3 minus 2 minus 1. What is 3? 3 is the value that comes out after calculating this. 2 is the value that comes out after this, and 1 is the value that comes out after this. So after you do this, you will get AD plus BC. This computation can be done in n by 2 order of time. Then you can just you will be getting this thing. This is the Gauss obtained after Gauss's trick, and then you can just follow the technique which was given in the first Karatsuba's version to calculate this A into B. Why? Because you have got an A, C, and BD, and AD plus BC. Now you just have to append this n number of zeros in front of AC, a n by 2 number of zeros in front of AD plus BC, and no number of zeros in front of BD. And after calculating that, you can just simply get AD A into B. Now, what is the time complexity of this algorithm? So this was the whole process. You get AC, you get BD, then you calculate this, then you compute this, you get AD plus BC. Then you appended 10 to the you append n zeros in front of AC, n by 2 zeros in front of this thing that you get in the step 4, and then you just add with BD. Now I will be discussing the time complexity for this entire process. So what you're doing, you are in how many scenarios are you doing multiplication? In the calculation of AC, BD, and this entire thing, you are doing overall 3 multiplications. So in the case of AC and BD, it is obvious there you are doing multiplication. But in the case of AB plus B and C plus D, you are calculating both of these things separately. And when you get those two things of the containing n by 2 number of digits, you just multiply both of them, and overall you are getting 3 multiplications. Now, therefore, we can say that the total number of work that is done in recursive calls is 3 into t of the order n by 2, and then we have to calculate the work done outside the recursive calls, and that is you just had to calculate this thing. In the worst case, this will take or the order of n time. Why? Because the all three of these are are numbers 3, 2, this 3, 1, and 2. All of them are numbers of the of containing n by 2 number of digits. So when you will do this calculation, in the worst case, you are doing n by 2 number of calculations. You just accommodate everything into C2 to just account for anything else that you are not including in the algorithm. and then you just add everything to get the time complexity of the entire thing. This is the same this C3 into n. This is the same thing that we got in the Karatsuba's first version, which was due to additions. So we just add all of these things together, and this is the time complexity for the second version of Karatsuba's. And this is the final recurrence relation. When you compare it to the first version, then in this case you can see that there are four recursive calls, and in the new version there are three recursive calls. So obviously this one is better. Uh, Basically, when we are comparing, we are just looking at this recursive version. This C2 plus C3 can be ignored because we can just take it as another C for an other constant, and it with the work done outside the recursive calls will be the same in both cases. We are here considering we are considering the work done in the recursive calls. In this case, there is three times the work done, and in the first version there are four times the work done, and hence this version is better. So this is the final version of Karatsuba's multiplication. I will just briefly go over it once again. You get two numbers. You have two numbers, capital A and capital B. You divide it into two n by 2 digit numbers, and you separate it into parts: small a, small b, small c, small d. These. Then capital A can be constructed in this way, hence, and capital B can be constructed in this way. And then you have to just get this formula. This should be n by 2. Then you just have to get this formula, and for to calculate this formula, you first calculate AC, then BD, then you apply the Gauss Trick to get AD plus BC, and then you just simply apply the formula after appending n zeros after this, and by two zeros after this, and no, you just add all of them. So this is the Karatsuba's multiplication. So we can see that this is a mechanical thing. All of this is automatic. It is unambiguous. There is no ambiguity. We are not confused. And of course, whenever you are coding and calculating, whenever you are dealing with computers, you cannot leave anything ambiguous. Otherwise, it will give you an error. It is it correct or is it efficient? Well, in most of the case, you will have to see whether the algorithm that you are designing is it correct first of all, because if it is not correct, then of course it is of no value. And after you get that it is correct, then you should make it with the most efficient thing. If somebody else brings something better than you, then also your algorithm loses value. So you must design a correct and an efficient thing. So how would this course now benefit you? It will first of all make you a better programmer. Algorithms are a very necessary thing in programming, and then it will improve your mathematical and analytical skills, and it will also help you prepare for the interviews. It will develop your algorithmic and mechanical thinking. It will help you become familiar with the greatest hits in the CS. And yeah, of course, you can always do research in theory of algorithms after this. So this is all that I have to cover in the multiplication. In the next video, I will be discussing the master's theorem. I will be discussing how to derive the master's theorem, and what is the use of master's theorem, several assumptions that I am assuming while creating it, while explaining it, and how is it useful, how integral it is, to calculate the time complexities in most of the scenarios. Thank you very much.